Okay, good morning. So let me begin by thanking the organizers, Yuval, Ganpathy, and Sumathi, for inviting me and giving me the opportunity to present some of my recent work here. And the first two talks in this session was on quantum information. Now in the third talk, we are back to condensed matter a little bit. And definitely there is an underlying motivation of topological superconductivity that deals with, again, quantum computation. But my objective is not that. My objective is to realize topological superconducting states, particularly in 2 dimension in this talk, using magnetic textures in heterostructures. So that, I mean, to propose something which may be close to experiment and whether possible realization. And this work that I am going to talk about is primarily done by my PhD student, Pritham. And the material realization, the first principle support is given by the PhD student in Niger. And also my previous PhD student, Arnob, who is in postdoc in Uppsala, he has also contributed a little bit in this project. And mainly, I mean, Ashish Nandi from Niger and myself has come up with this project. So, and so my talk will be based on this, basically these two works. So both of them are under review. So if you want to look at the details, you can look at this paper if you have got interested. And so what is the outline? The outline will be, because I am talking about topological superconductivity and which deals with the Majorana modes. So first, I think we should have a slight background on the Majorana, and then I will talk about first the first order topological superconductivity, the 2D heterostructure with non-collinear magnetic texture, and then we'll see that how much time we have, probably if not in details, but I will try to flash how to obtain the second order topological superconductivity. And at the end, we will summarize and conclude. Okay, so just to define Majorana, so Majoranas are some electrically neutral particles, which are of their own antiparticle. So they satisfy this relation gamma is equal to gamma dagger. So one of the interests to find the signature or the appearance of Majorana, to realize Majorana in solid state system, is its possible application in making qubits for topological quantum computation. So in quantum computation, the Majoranas are believed to be one of the building blocks. So anyway, my objective will be to understand the rather topological superconducting phase and how to realize Majorana. So these are some reviews. You can look at it. So to start with, let us first, before going to 2D, let us just try to flash that what happens in 1D. So which starts with the famous Kitaev model. So in the Kitaev model, you can see that this is a tight binding model with a p-wave superconductivity, because this is the nearest neighbor pairing. Yeah, this is the hopping term. You have a chemical potential. And so not going into the much details, but this model can have two phases. So in one of the phase, you can see that if you write each fermion in terms of 2 Majorana, if you go to a different basis, Majorana basis, then you can see that here intermediate states, they are here everywhere. Actually, it's a trivial phase, because you can see that at each lattice sides, the 2 Majoranas have coupled and forms a fermion. But you can have a non-trivial phase where you can see that you have 2 unpaired Majoranas sitting at the two ends of this chain, 1D chain. Okay. So with this two unpaired Majorana, I can form a non-local state, which is, you can think like a qubit state. And from here, so the first, I mean, at least I would say that 1D setup, simple setup, the Majorana can be, I mean, theoretically predicted. But the issue is that the one, I mean, this is a very toy model. So the objective is to engineer this kind of p-wave superconductivity, which hosts Majorana in a more realistic model setup. Okay, which can have more experimental realizability. So there are different proposals. So one of the famous proposal is Rashba nanowire, which I am not going to discuss. So rather, I am going to discuss another setup in one dimension, which deals with magnetic impurities. Okay. So you can see that if you have magnetic impurities in a superconductor, so if you suppose you have a 2D superconductor and you somehow engineer 1D magnetic atoms. So in this Hamiltonian, you have a hopping, then you have this magnetic impurities. So, but the magnetic impurities is such that at each lattice sites, they have different orientation. Okay. So they are somewhat non-collinear. And you have a S-wave superconductor, which is easily available to us. Okay. And so what happens is that suppose if you have one magnetic impurity in a superconductor, so this magnetic impurity locally can break the Cooper pair, and then electron can scatter with that magnetic impurity, can give rise to in-gap states, so which are called Shiba states or YSR state. So, but now if you have many magnetic impurity, even let's say classical here, so these so Shiba states formed due to many magnetic impurities and start overlapping and can give rise to a band which is called Shiba band. Okay. So suppose if I do suppose if I do a exact diagonalization of this model, which is done in these papers starting in 2013. So then what happens is that, I mean, so you have, if you plot the eigenvalue spectrum as a function of the strength of this magnetic impurities, then you will see that you start getting a Majorana mode in this region. So, and here the bulk spectrum is gapped, but within the bulk at zero energy, you have topological mode, which is the Majorana. And if you also see the local density of states at the end of the chain, you can see that the local density. So this is a quasi 1D setup. You can see that you have the signature of Majorana is emerging at the end of the chain. And now if you measure the local density of state at the middle, then you get the signature of this YSR Shiba state. So also, if you look at the local density of state as a function of energy, so what happens is that within the Shiba band, you formed a mini gap, and the sign change of this mini gap gives rise to a topological phase transition in a Majorana within the mini gap. So this is zero energy states in the local density of state. So this peak again designates in a STM setup, designates the signature of Majorana. And also evidently in the middle of the chain, there is no Majorana, but you have signature of the Shiba bands or Shiba states. So soon after the, I mean, and concurrently, also the first experimental proposals came in 2014 from the Ali Yazdani's group, where they have taken, they have designed actually 1D ferromagnetic atoms on a dead superconductor. Okay. And in this experiment, so here I'm showing the differential conductance, which is the proportional to the local density of states. as a function of energy. So you can see that if you look at here in the experiment, so if you measure the LDOS at the two end of this chain, like in this red spots, so 7 here they can see that they have a small zero bias peak. So, and again that they have emphasized more in this inset. So, their prediction is that this zero bias peak due to Majorana. And on the other hand, if you measure your LDOS or DIDV at anywhere at the middle of the chain, for example, here, so there is no Majorana, but these peaks are due to the Shiba states. And there are some more recent experiments. So, in which other more simplified systems like manganese on a niobium or chromium in a niobium. So, they are also not topological superconductivity, but this formation of quasar states has been predicted in experiment. So, these are mostly experiment has been done in a superconductor and depositing one chain of magnetic impurities on top of that. Okay, so now so far 1D, but if I go to the 2D, the version of the TIFR model, so 1D we have seen that we have two N modes, Majorana N modes at the end of the chain. But if you take a 2D version of the same TIFR model with a P wave superconductivity, so then this theoretical model can have, so far in the 1D model we have seen gapped topological phase, but in this 2D TIFR model, theoretically, just if I solve the model, so then if I can have a gapless topological superconducting phase. Yeah. So these 2 points, yeah, like two vortices, and this gapless topological superconducting phase, if I solve a ribbon geometry, so I can see that, so this gapless phase hosts a flat Majorana edge mode. It is a flat mode, it's not dispersive. And even in the eigenvalue spectrum, if you take a finite lattice system, open boundary condition, so they have shown that there is a flat Majorana mode at 0 energy. So now this is a fully theoretical construction. So first we try to ask the question that suppose if I generalize my 1D spin chain system in a 2D with a SOF superconductor, then using SOF superconductor which is available to us and magnetic impurity, can I design the Majorana flat mode? And if yes, and can we support some material realization to understand this flat mode in our geometry? So that was the motivation. So yeah, but I need to go to the. So before understanding the full results of the lattice model with material support, first we can try to understand this physics from the low energy sector. So if you write the low energy sector of this Hamiltonian, so this like kinetic energy, and you have this pairing term and the magnetic impurity. So I can do a unitary transformation and one can develop a effective Hamiltonian in the low energy sector. And from this low energy effective Hamiltonian, one can understand that this spin spiral is giving rise to the kind of spin orbit coupling and some effective Zeeman field or effective magnetic field. So, and this spin orbit coupling depends on the pitch vector of your spin spiral, and the effective Zeeman field depends on your strength of the impurity. And if you look at the bulk density, bulk spectrum and density of state of this Hamiltonian, then the bulk one can understand that. So here, this is the trivial gap topology. And then if you change this magnetic exchange at some critical value of this J, you will have band closing. And but greater than this JC, you will have two gapless points in the bulk. So in the density of state also, from a gap density of state, somewhere you are reaching to a semi-metallic kind of density of state within the, I would say, within the Shiba band. So now, so this is the bulk which mimics the 2D theta model physics. So now if I do the, so for this gapless phase, I can also locally define a invariant, so which is like, so this invariant tells me that this is a weak topological system because I have two nodes at the bulk, and it is not difficult to destroy this scattering, I mean introduce scattering and destroy them, but we can see that where this at least this gapless phase is stable in the parameter space, one can find. And not only that, if I find the spectral function of our model, then the spectral function you can show that from a gapped phase, trivially gapped phase, I can go to a gapless phase with a flat edge mode at the boundary. Fine. So from the theoretical model, it's fine. So now I contacted my collaborator in the NISER. So what they have done for us is that, so from a material, so the material is what? So they have taken a manganese niobium film. So from the real atomistic calculation, from this, starting from this Hamiltonian, so they have given a ground state to us, which the ground state is antiferromagnetic spin spiral from that DFT calculation. So this is a purely like in the theoretical analysis, we are showing the spin spiral. So here also you can see that in a real material point of view, one can generate this spin spiral structure. So now if you take this spin spiral structure and incorporate this spin spiral structure as the texture in your lattice Hamiltonian, and again if you do a exact diagonalization based on this spin texture that has been generated from the same films, so you can see that again in my eigenvalue spectrum in the topological mode, you have this flat mode at the boundary, and in the non-topological phase you have nothing. It's a gapped non-topological phase. And also if you look at the minimal gap, so this gap, let's say, as a function of the parameter space, chemical potential and the strength of this field, magnetic impurity, then you can see that here, this is the topological phase in the phase diagram. So within this phase, you have this, this is gapless in the bulk, but you have the edge mode, which is flat at the boundary. So not only from theoretical model, but also from a material point of view or some material support, we can try to establish that, okay, this 2D topological superconductivity, the gapless topological superconductivity posting the flat mode can be supported. So which was prediction of a pure theoretical 2D type model, but with the help of SOF superconductivity and manganese. So both the things are easily available in the lab. Probably one can try to design a Shiba lattice, 2D Shiba lattice, where these edge modes one can try to find in experiment, either in the STM or via the RPS. So this is so far for the, and this is the first order topology, topological superconductor that I have talked about so far. So Ganpathy, I am going about the time.
You have 3 minutes of regular time and then you should have a 5
Okay,
minutes.
then I'll be fine. Okay, great. So in the second work, so after doing the first order topology, we went to a second order topology. So in the first order topology, like if you think about D is the dimension of your system and N is the order of your topology. So far you can see that my D was 2 and N was 1 because I always have 1D H states. But now I will talk about a system where your D is 2 and also the order of your topology is n is equal to also 2, such that, so 2 minus 2, so as a boundary mode, you don't have edge, but you have corner. Okay, so we'll try to give you a model. At least in this model, we don't have material support, but at least theoretically, I can try to give you a model where you can realize that corner modes at the end. So these corner modes are called the Majorana corner modes. So which I call Majorana edge mode. Now I'm calling it Majorana corner mode because it's the second order topology. The bulk properties are bulk characterization will be different here. So what is the lattice Hamiltonian for it? So again, you have a we have a SOF superconductor, and so you can see that this is a SOF superconductor, and on top of it you have a 2D topological insulator. So one quantum Spielhorn insulator, and then on top of it you have this spin spiral. So the Hamiltonian tells me that I have a SOF superconducting pairing. So this is exchange field strength, but this cos phi ij, it's giving me that at each side the angle of your spin is different, so that you have a texture. And and this intrinsic spin orbit coupling is coming from the quantum Spielhorn insulator. Okay. So I have 3 ingredients now. So this quantum Spielhorn insulator as material you can think about like mercury, right? So now if I first see the results for my exact diagonalization, then you can see that in your eigenvalue spectrum, there are 4 zero modes. And if I see the local density of states, then you can see that these 4 modes are sitting at the corners of the system. And also, if I, again, the eigenvalue spectrum, if I see as a function of the pitch of my spin spiral, then you can see there is a critical value of this G. After that, this second order phase will break and you will have a gap. But so within this regime, you will have the second order phase. That means within this pitch vector, within this value of the pitch vector, your Majorana mode, Majorana corner mode will survive. So, and in our theoretical analysis, the pitch is varying diagonally like this. Okay, so I have to wrap up in 5 minutes. So so this second order phase, one can usually, I mean, we have to characterize this topological character that I can do by a quadrupole moment. And this quadrupole moment, if you see as a function of the pitch vector and the spin orbit coupling, you will see that this is the topological regime from real space. And this is also from the effective model that I don't have time to go into. But you can see that this is my topological regime. If I, in different parameter space, where in the topological regime, this quadrupole moment becomes 0.5. And in the trivial regime, it's 0. So this is the characterization of your second order topological phase, which is very different than the first order topological phase. And why this corner modes is appearing, we can have slight more insight also from the edge picture. So I can develop a theory starting from the bulk. I can develop a low energy edge theory. And if you look at the, so suppose if you name these edges as 1, 2, 3, 4. So if you see that, if you look at this edge 1 and edge 2, so if you derive that, after deriving that, if you see the mass gap of edge 1, you can see this mass gap is actually proportional to this parameter. But if you see the mass gap of the second edge, then you can see that there is a competition. And the mass gap of the second edge, I can change sign by varying the exchange. Okay, so there can be a sign change of mass gap at the second edge, depending on this parameter. So now, if the mass gap here, if it is completely positive, but if I can make this mass gap along 2 as negative, so then I know that this positive and negative mass, according to Chakourebi theorem, will give me a 0 mode at the corner. So from the bulk and also from the edge, so because second order topology definition is that your bulk is also gap and the edge is also gap. So bulk will you have to characterize by this quadruple moment where the bulk band inversion will be there. And also at the edges, you have different mass sign change. For that reason, you can have this appearance of the Majorana mode. So both bulk and edge one has to see. And also there are another way to see the effective pairing in this second order phase. If I do a dual transformation, and I can, by this unitary transformation, I can write a dual Hamiltonian. So by doing this dual Hamiltonian, I can try to predict that in here, the effective pairing has two kinds of pairing I have. So one kind of pairing is Px plus IPy, which is proportional to the intrinsic spin orbit coupling of the quantum spin Hall. On the other hand, you will have a delta Px plus Py type pairing, which is proportional to the pitch vector of the impurity. And these two types of pairing actually is responsible for the two types of bulk pairing is responsible for having this second order phase in the bulk. So, okay, so what is the take home message? So far I try to convince you that after one dimension, so I can try to develop or 2D topological superconductivity based on this non-collinear magnetic textures. So first, I try to show you that the topological superconducting state with a Majorana flat edge mode and based on some material support, basically manganese and niobium, I try to give you that these flat modes are quite stable and can be possible to realize. And in the second proposal, which is mostly theoretical, I try to show you that based on a topological, to generate a second order topological superconductor hosting Majorana modes by this magnetic texture, quantum spin Hall and S-wave superconducting hybrid system. And so currently the issues we are working on that, so this topological superconductivity, whether can be engineered with skyrmions or anti-skyrmions, and also how to do braiding protocol with this order modes or the second order topological systems.
Okay, let's thank Arijit.
Yeah, sorry.